Hi guys, I'm Abhinav. I'm going to talk about our paper on testing and robust characterizations of convexity. It's joint work with Eric Blake. Let me start off by defining what convex sets are. Before that, throughout this talk, I'll be using bodies for compact sets. So whenever I say body, I mean a compact set. And yeah, so the most common definition of convexity is a body is convex if any 2 points you take in the body, the line joining those 2 points lies completely inside the body. And here we're talking about sets in n-dimensional space, and you can assume n to be a really, really large number. And here's an example of a convex body and a non-convex body. In the convex body, any 2 points you take, the line is completely inside. And in non-convex body, there exist points where the line goes outside the body. This definition can be extended to more than 2 points, where you can say a body is convex if and only if for any set of points that belong to the body, if the convex hull also belongs to the body. Again, the same examples, you can see that you take any set of points in the convex body, the convex hull lies completely inside, and in the non-convex body, there exists points that are inside the body, but the convex hull still goes outside the body. Here, in this paper, we deal with the question of geometric convexity testing. And broadly, geometric convexity testing tries to answer the question, given an unknown body, can we determine, how efficiently can we determine if it is convex or not? Like the first question that would pop up into your mind would be, what do you mean by giving an unknown body? How can we access it? What is the model you're talking about? And so let me first define what is the model. So you're given the body and you're given access to two oracles for the body. So you don't know the body, you're just given these two oracles. The first oracle is the random oracle, which when you query, gives you a point from the body uniformly at random. So whenever you query, you get a point uniformly at random. And then there's the membership oracle, which when you query at a point, it tells you if the point belongs to the body or not. So that's how you can access the body. And with these, can we answer the previous question? How efficiently can we tell if the body is convex or not? There are some examples where it's almost impossible to tell if it's convex or not. For example, here you take a convex body and just remove 1 point. It's almost impossible to tell if it's convex or not. So we try to we try to consider a more relaxed a relaxation of the problem, where instead of trying to determine if the body is convex or not convex, we try to determine if it is convex or far from convex, and we need to answer correctly with only probability 2/3. And what do we mean by far from convex? We say a body is epsilon far from convex if for every convex body, the volume of the symmetric difference between the body K and the convex body is greater than epsilon times volume of K. That's a formal definition. What it essentially means is you have a body K, and if you want to change it into any convex body C, you have to change at least epsilon fraction of volume of K. That is the total volume which you delete from K and that volume you add to K to make it convex is at least epsilon times the volume of K. So this is the formal statement of the geometric testing, convexity testing problem. So how efficiently can you determine if a body is convex or far from convex with probability 2/3? And the major open question in this area is, can we do it using polynomial number of queries? So first, there are two natural testing algorithms which people have considered. One is the line test and the other one is the convex hull test. Let's look at both the algorithms and see if they're efficient or not. So first, let's define what the line test is. You're given this unknown body. What you do is you just query 2 points at random and then check if the line lies inside the body using the membership oracle. And you keep repeating this. And at some point, if you find a line that goes outside the body, then you stop and say the body is not convex. Otherwise, after repeating it for some number of times, if all the lines still lie inside, you say the body is convex. In Rademacher and Mempala in 2004, in their paper, they showed that there exists a body that is 1 over n square far from convex, for which you take 2 points. The probability that the line joining those 2 points going out is like extremely low, exponentially low. Let's look at what their proof idea was. So this is the example which they used to prove this theorem. So it's called the Elven Ball with peaks. You first start with an Elven ball and then extend the faces so that you get the peaks. And they show that this body is 1 over n square far from convex. And this body has the property that like any 2 points you take inside the body, the line lies inside the body, except when you take 2 points from adjacent peaks, then the line goes outside the body. So if you pick 2 points uniformly at random, the probability that you get points from adjacent peaks is exponentially low. That's the reason they get this theorem. So because the probability that the line goes out is exponentially low, if you want the line test to work for this particular example, your query complexity would be exponential in n. So does that mean the line test is inefficient? It's not entirely clear from this theorem because it doesn't rule out query complexities like n to the power n into 2 to the power 1 over square root epsilon. Here in this example, epsilon is 1 over n squared. So if you substitute epsilon 1 over n squared, you get the query complexity to be exponential. So because here epsilon is extremely small, it's not clear if you're getting the exponential query complexity because of the epsilon or n. So it could still well be that it's linear in n and exponential in epsilon. In our first theorem, we show that's not possible, that you have bodies that are actually one constant far from convex, and the probability that the line joining those two random points going out of the body is extremely low. So this rules out the line test. And so what else can we do? The other one is the natural convex hull test, which is an extension of the line test. Let me describe what it is. Here, instead of picking 2 points, you just pick a set of points uniformly at random by querying the random oracle, and then check if the convex hull joining these points, if it goes outside the body. You check this using the membership oracle, and you keep repeating this till you find a convex hull that goes outside the body. This test has been found to be effective in lower dimensions. Berman et al. have come up with algorithms which work in lower dimensions, which are quite similar to the convex hull test. But in higher dimensions, we show that the same body which we had for theorem 1.1, which is 1 over 8 far from convex, there, even if you take exponential number of points from the body uniformly at random, the probability that the convex hull of the points going outside the body is extremely low. So this even rules out the natural convex hull test for our setting. So here is the summary of our results. These are the theorems. But what we have essentially proved in these theorems is that the characterizations which we mentioned at the very beginning of our talk the line characterization and the convex cell characterization of convexity are not robust. That is, we have given examples of bodies that are far from convex, but which almost always satisfy the characterization. So the characterization is not robust. So here there are like two questions which have come up so far. One is the main open problem, that is, can you solve the geometric testing, geometric convexity testing problem using polynomial queries in membership, using membership oracle and random oracle? We have shown that at least the natural algorithms which people have tried so far wouldn't result in that. People have to come up with something entirely new for this. And also we've seen the two natural characterizations are not robust. Are there any other characterizations of convexity that are robust? Like there's a link between these two questions. If you are able to come up with a characterization of convexity that is robust, that might lead you to a tester. Now let's get started with the proofs. So the proof of theorem 1.1, it essentially has three steps. First, we define what our body is, that is 1/8 far from convex. Then the second step is to show that it is actually 1/8 far from convex. And then the third one, to show that the line joining two random points going out, the probability is extremely low. Here is a body D. We get this by, this is an n-1 dimensional ball of radius 1.1. This is an n-1 dimensional ball of radius 1. And this is an n-1 dimensional ball of radius 1.1, which are placed at, this is placed at D, 0, and minus D. That's all these points on this ball have x equal to minus D. Here x equal to Z, and x equal 0, and x equal to T. And you take the convex cell of the left, the left ball with the center ball, and the convex cell of the right ball with the center ball. The body we get by taking these convex cells is what we call union of two truncated cones. Why do we call this union of two truncated cones? So each half of this, if you look at it, is a truncated cone. If you extend these lines, they meet at some point, and what you get is a cone. So by cutting the cone, you get this truncated cone, and you take the union, and that's our body. Now let's move on to step 2, where we show that the body is 1/8 far from convex. The proof of step 2 has again three sub steps which we prove. First one is we show that the closest convex body to D is symmetric about the axis. And next we show that it's not only symmetric about the axis, but also the closest convex body is a truncated cone. And then third, we show that every truncated cone is far from our body. So essentially, because truncated cone is the closest convex body, and every truncated cone is far from our body, so our body is far from being convex. So first, proving 2.1. Let's assume that the closest convex body is not symmetric. Let C be the closest convex body. And now what we do is we take slices of these body of C at each x equal to T, and we apply something called Schwartz symmetrization, which, so the slice of C at T would be CT. Now we replace this CT, so this would be an n-1 dimensional body, same as dt, which would be an n-1 dimensional body. So you replace CT with CST, which is a ball of such that the volume of CT is same as the volume of CST. And you do that for all T. Here, it's easy to observe that distance between dt and CT is greater than or equal to difference between the volumes, because here difference between the volumes would be, the distance between these two bodies would be this area plus this, which is the symmetric difference. but the difference in volumes would be strictly less than this. So you can see that the symmetric difference is greater than difference in volumes. But whereas in the second case, because both of them are balls, the volume of symmetric difference would be exactly same as difference in volumes. So we get that distance between dt and ct is greater than or equal to distance between dt and cst. This is for all t. So essentially what we are getting is distance between d and c, which is the initial convex body we started with, is greater than or equal to distance between d and cs, where cs is a symmetric convex body. And so now this here we haven't completed the proof of 2.1 because we have shown that cs is closer to d, but we are yet to show that cs is convex. For that, we'll be using Brun's theorem from convex geometry, which says if you plot the radius graph of cs with respect to x, you get a concave function. And this combined with the lemma which we prove, which says any body that is symmetric about the axis and the radius function is concave, the body is convex. So combining this with our CS being concave, we get that CS is concave. Sorry, CS is convex. So we've proved. So here we've proved the first part where the closest convex body is symmetric. Next, we need to prove that it's also it's actually a truncated cone. So let RCS be the graph of the symmetric radius graph of the symmetric convex body, and RD be the radius graph of the body D. They would, because this is concave and this is convex, they would intersect at 2 points P1 and P2. Now draw a line joining P1 and P2, and let that function be RCC. This radius function would define a truncated cone because the radius is changing linearly. This would be a truncated cone. And now we are going to prove that distance between this truncated cone and our body D is actually less than or equal to distance between the symmetric body and D. So here let's look at between P1 and P2. Here distance between D and the truncated cone would be, so this is D and this is the truncated cone. The distance would be this volume essentially. It would be this. And here the distance would be this area because this is CS and this is D. So that here clearly it is a subset, the distance between the truncated cone and D is a subset of the distance between the symmetric body and D. Similarly, between P2 and D, here we have the distance between D and the truncated cone is this area, and distance between D and the symmetric body is this. Again, distance between D and symmetric body is larger, even in between P2 and D. Similarly, we can observe that between P1 and minus D. So essentially, everywhere between minus D and D, CC is closer to D than CS. So that would prove this. Next, this is the last step for proving step 2. Here we show that every truncated cone is far from convex. Before we prove this, we need to know a fact from convex geometry that let's say I have a ball of radius 1.1 and a ball of radius 1. This is in n dimensions. Then the ratio of their volumes, the ball 1 would be exponentially larger than ball 2. So you can think of volume of ball 2 being almost 0 compared to volume of ball 1. So because of this property in higher dimensions, the volume distribution of our body D would look something like this. If you divide this into 4 quarters, almost all the volume, half the volume would be in the first quarter and half the volume would be in the last quarter, and the volume in between would essentially be 0. Now, let's take any truncated cone and split it into 4 quarters, similar to what we did with our body D. And because the radius is increasing, we have the volumes in an increasing order V1 to V4. Now, the distance between D and CC would be, if you look at just the left half, it would be greater than V2 minus V1 and sorry, V1 minus V over 2 and V2. So this would be, the distance would be greater than this. And let's split it into two cases where first case V1 is greater than V over 4. Then because V2 is greater than V1, you have V2 is greater than V over 4. So that says that distance between D and CC is greater than V over 4. Similarly, even when V1 is less than V over 4, we have here the first part would be greater than V over 4. So in both cases, we'd get the distance between D and CC is greater than V over 4, which is 1 over 4 times volume of D. So that shows that the body D is 1 over 4 far from the truncated cone. Here it says approximately, because if we write down the actual numbers, what we end up with is we'll have 1 over 4 minus small o of 1. So to be safe, we just have 1 over 8 far here. It's actually almost 1 over 4 far according to this proof. Now we have defined the body, we have shown it's far from convex. So we have proved this statement. All we are left to prove is to show that you take any 2 points, the line lies inside the body with almost probability 1, that it goes outside with negligible probability. For that, again, you need another fact from convex geometry, which says if you take a ball of radius 1 and let V1 be the volume of the body, which is at a distance of 0.1 from the equator, then volume of V1 versus volume of V, which is the total volume of the total ball, is almost 1. That is, most of the volume is concentrated very close to the equator. So rest of the volume combined is just an exponentially small fraction of the total volume. So because of this, what happens is, though a point is, well, it won't be like a line joining this with any of the points here would go outside the body, but volume of the points here is almost 0, because from the previous fact we proved, we have almost all the volume lying in this area close to the axis, close to the equator, and all these points, for all these points, the line joining this with any of the points here will lie entirely inside the body. That's the intuition. The details are in the paper and they're easy to follow. And the proof of theorem 1.2 mainly uses theorem 1.1 with an additional lemma, which we prove that, let's say you have a set of points where line connecting any 2 points in the set lies completely inside the body, then the convex hull of the points also lies completely inside the body. So combining this lemma with theorem 1.1 and using union bound would essentially prove this theorem. Yeah, the end.